I want to show you a new type of probability distribution, which is called chi-squared. Here I have a random code. I just copied and pasted from online that shows you a normal distribution. And I think this should be 0 and 1. Okay, so let's see. What does that do? All right. So you see this, the usual normal distribution. It's only 250, so that's not good. Let me increase this to 1,000,000 maybe. And there might 100,000. Okay. Let's see. Let's see if we get a nice looking bell curve. Okay, that looks more like a bell curve. Let me increase the bin size to maybe 200 or maybe 201. All right, that looks better. Okay. So this is your normal, usual bell curve, and let me just give you a quick explanation of this code. So NumPy has a function called random.normal, which gives you random variables from a normal distribution with average and standard deviation given like this. Since average is 0 and standard deviation is 1, what we have is a standard normal distribution. And I'm generating 100,000s of numbers from that. And from that 100,000 numbers it randomly generated, I'm using the matplotlib library to plot the histogram of this randomly generated one. And as you can see, you would get this nice looking bell curve. And of course, the more samples we take, it's going to look more like a smoothed one. So if I put one extra 0, then let's see what happens. Yep, it's a nicer looking bell curve. So this is what's known as the normal distribution, right? The normal distribution has the formula something like e to the negative x squared over some number. So it decreases a square of exponentially as you go right or the left. Now, what I want to do is I want to now use the same data but plot the data squared. So what I'm going to do is I'm going to square all the values in this data, and let me show what happens. And this is rather, it doesn't look that pretty, but that has a name. This graph is what's called a chi-square distribution with degrees of freedom k equals to 1. So let me just write it here. This is a chi-squared distribution with degrees of freedom k equals to 1. And so here's how you think about it. Some numbers will be pretty big, right? Just by chance, you might have numbers that reach up to 4, and those squared will give you very high numbers, something as high as 16, but they rarely occur, right? Most of the numbers are somewhere here. And since 68% of the data falls between -1 to +1, more than 2/3 have values less or equal to 1, and if you square it, it gets even smaller, right? If you have, for example, if you have a random number 0.5, if you square it, it becomes even smaller. It becomes 0.25, so it gets closer to the left side, right? So that's what's being graphed here. And you use this chi-square distribution if you have a question about the variance that is, like if you take a random sample and you have a question about whether this variance looks all right or not, you use the chi-square distribution, okay? Let me give you another one. So this time I'm going to sample data 1 and data 2. Okay. So I'm going to copy this one. I'll call this as data 1. And I'll call the second one as data 2. So I have samples that are independently generated, okay, randomly generated. Data 1 and data 2 do not know about each other. They're completely random. They're independent of each other. And then what I want to do is I want to take the square of data 1 and also the square of data 2 and add them together and draw the same kind of graph. Let me show you. Let me see. So over here, instead of data, I have data 1 squared plus data 2 squared. And let's graph it. And now you have, again, similarly looking, but now you have more things on this side, right? What if I have another one, data 3? So if I have data, well, let's go with data 3 and 4, okay? So this one here is 2 degrees of freedom, but I'm going to now generate the chi-square distribution with 4 degrees of freedom. So I'm going to add 2 more things here. So data 3, data 4. So I have 4 independent random variables who are normal distribution, but I'm squaring these values and I'm adding them, okay? And this is going to give us, because I'm adding 4 things, now the degrees of freedom will be 4. Okay, so this is what you get. Now, can you guess what's going to happen if you add more and more?
It's going to turn into a bell curve.
Huh?
It's going to turn into a bell curve.
It will again turn into a bell curve. Why? Why is that? Because of?
The degrees of freedom.
No, because of some theorem. Huh? Central limit theorem, not that one. Central limit theorem. So what does the central limit theorem say? If you have independent and identically distributed random variables and you keep adding them, actually it says you take the averages, but like averages only rescale. The shape doesn't change, right? Yeah. So if you just keep adding them, they become more and more like a bell curve. Okay? So you can kind of see that as you increase the k value, this is going to get closer and closer to a bell curve. So for a very high k value, you may be able to just use the normal distribution instead of the chi-squared. But usually, you get to use the chi-squared distribution for smaller degrees of freedom. So these will be important. Okay. Anytime we want to draw inference from the variance of the sample, we have to use chi-squared.